Dear friends, today we have a new topic of thermodynamic stability of water. The pH and potential under which water is found to be stable in our surroundings. Actually, water is an amphoteric compound capable to act as oxidizing agent as well as reducing agent. Suppose our water is in contact with a species of negative reduction potential, extremely low reduction potential, such as sodium or potassium ion. That metal can act as a reducing agent. Here you first remember the fact that the elements with low reduction potentials are better reducing agents and high reduction potentials are strong oxidizing agents that we have discussed in electrochemical series. So, if a metal or any species of highly negative reduction potential fall into the water or come in contact with water, that species act as a reducing agent and it can reduce water to hydrogen. That species which is going to act as a reducing agent donate electron to water. The H plus ion in water accept that electrons from that reducing agent and reduction of H plus ion takes place to hydrogen. An equation can be given as 2H plus 2 electron gives H2. Here E0 is found to be 0. When water is in contact with a species of high reduction potential, species with high reduction potential are good oxidizing agents. So, when water is come in contact with such a species, negatively charged oxygen will donate electron to that oxidizing agent. Oxidizing agent is electron absorber. So, oxygen in water donate its electron and undergo oxidation to O2. Equation 2H2O gives O2 plus 4H plus 4 electron. So, the species with low reduction potential reduce water to hydrogen. At the same time, species with very high reduction potential oxidize water to oxygen. Here E0 is found to be 1.23 volt. So, definitely there is a boundary of water stability. It can be explained as follows. When water acts as an oxidizing agent, reduction of H plus takes place to hydrogen as shown in this equation. Suppose partial pressure of hydrogen is 1 atm and temperature is 25 degrees Celsius, then this reaction 2H plus 2 electron gives H2, equation number 1. Here N is found to be 2. Nernst equation for this reaction can be given like this: E equal to E0 plus RT by 2F log ln H plus square by partial pressure of hydrogen. Since we are putting positive sign here, we have to write oxidized species on the numerator, that is H plus, and reduced species in the denominator H2. Since partial pressure of hydrogen is 1, this can be taken as 1. Then E0 plus 2.303 RT by 2F log H plus square. then taking h plus square log, then you will get 2 log h plus, and solving, finally you will get E0 minus 0.05911 log 1 by h plus. By putting plus to minus, log h plus become log 1 by h plus. Log 1 by h plus is actually pH. So we can write it as pH. E0 is 0 for hydrogen. So equation become minus 0.0591 millivolt into pH. This is an important equation which we have numbered as 3. E equal to minus 0.0591 millivolt into pH. This equation clearly indicates that potential of the system will decrease by 0.059 millivolt for every 1 unit increase in pH. When pH equal to 0, potential equal to 0. When pH equal to 1, it become minus 0.0591. If pH equal to 2, it become minus 0.0591 into 2. If it is 13, then it become 0.0591 into 13. So slowly decreases with increase in pH. This is the case of hydrogen liberation, or it is the condition when water act as an oxidizing agent. Now we have to consider other end. When water acts as reducing agent, oxidation of O2 minus oxide ion to oxygen can happen. Consider that reaction. O2 plus 4H plus 4 electron gives 2H2O. Write this equation written in this form. We have told that it is the process in which water split into oxygen, but equation is the formation of water from oxygen. So equation can be written in the reduction form because we are writing reduction potential. So by applying next equation, we will get partial pressure of O2 into H plus raised to 4 by partial pressure of H2O. By putting this and this 1, we will get log H plus raised to 4. This 4 and this 4 cancel, and finally we will get 1.23. Here once we have mentioned the value, it is 1.23 is the E0 value. 1.23 minus 0.0591 log 1 by H plus. What is log 1 by H plus? That is pH. This is equation. So for every 1 degree increase in pH, E value decreases by 0.0591 from 1.23. Here it was from 0. Here it is from 1.23. Since E0 is 1.23. So at pH equal to 0, this term becomes 0 and E become 1.23. This is another fundamental equation which we have numbered 5. One equation we have numbered 3 in the previous slide. That is also important. That was for hydrogen, it is for oxygen. Thermodynamic stability of ion. It is dependable on many factors such as solvent, other solute present in the solution, and presence of dissolved oxygen. This graph is an important one to explain the stability of water. As far as concerned with H2O hydrogen reaction, when hydrogen is formed from water, when it is come in contact with a good reducing agent, they can reduce water to hydrogen. At that condition, E at pH equal to 0, pH equal to 0, E is found to be 0. when pH equal to 1, it is found to be minus 0.0591, 2, then 0.0591 into 2, and so on. That value is plotted in this graph. pH equal to 0, it is 0, then minus 0.0591, then slowly it decreases up to 14. Then we will get a straight line as shown here, which we can number as 1. In the same way, for oxygen liberation from water, O2 H2O coupled, when pH equal to 0, value is 1.23. 1.23, that is here. Then for every 1 unit increase in pH, value decreases by 0.0591. So decrease is same here and here. So the line has same slope as the line 1 and goes on decreasing up to pH equal to 14, and it can be numbered 2. So we have two lines, 1 and 2, one for hydrogen liberation and second for oxygen liberation. From this graph itself, reducing condition is present at the lower part and oxidizing condition is present in the upper part. As the electrode potential increases, reducing power decreases while oxidizing power increases. Good oxidizing agents are at the higher reduction potential and good reducing agents are at the bottom part. A reducing agent which can reduce water to hydrogen, or any oxidizing agent which can oxidize water to oxygen, cannot survive in water. So when a species having electrode potential greater than that represented in this line, sorry, not greater than, less than the potential represented in this line number 1, then they will come in this region. Okay, in that region they will reduce water, so water has no stability in this area. When a species of highly positive electrode potentials, which is greater than the potential represented by the number second line, that I mean in this region, they will oxidize water to oxygen. They are good oxidizing agents and they can oxidize water to oxygen. There also water is unstable. So the only stability is possible in this mid area. This is the stability region. Any species which has a potential less than potentially given by equation number 3. I once you told that equation number 3 is an important equation which is equal which represent E equal to minus 0.0591 by millivolt into pH will reduce water to hydrogen. But even if the theoretical value is this line, actually no evolution of hydrogen from water takes place at this potential. It actually happen at a higher potential around 0.5 to 0.6 volt due to kinetic factors and over voltage. A clear margin of 0.5 to 0.6 volt is necessary for H2 evolution, which actually they tell. They clearly explain the reality that from this graph we are expecting a species with minus 0.2, not minus 2, minus 0.2 volt, minus 0.2 volt is capable to release hydrogen from water by reducing it, since that species is a reducing agent. But actually that species is incapable. In practical condition, this is not possible if they have potential less than this line. I mean around 0.6 or 0.62 volt. Then they will reduce water and liberate hydrogen. So this region is also found to be stability region for water due to our potential and some other kinetic parameters. The same thing happen in the oxygen liberation case also. Here we are expecting at 1.2 volt, 1.23 volt, but the real liberation of oxygen, release of oxygen happen at higher potential around 0.5 to 0.6 volt. I mean 1.7, this line. So here also water is found to be stable in many conditions due to our voltage. If there is no our voltage, then things can happen at this line itself. Any species which has a potential greater than the potential of equation 5, that is for oxygen, will oxidize water to oxygen. Here we are discussing about the upper end, this side. Strong positive 1.23 volt indicate that for oxygen water coupled, oxidation potential is found to be 1.23 volt, which is a high value. That means water is a good oxidizing agent. But when water comes in contact with a better oxidizing agent than water, then water get oxidized to oxygen. Example, cobalt 3 plus is a good oxidizing agent than water. It can oxidize water to oxygen because E0 for cobalt 3 plus 2 plus couple is 1.97. It is greater than 1.23 and it is greater than 1.73 also. We are expecting an increase in voltage of around 0.5 volt to 0.6 volt due to our potential. Here 1.92 is the potential for cobalt. For water it is 1.23, then difference is 0.69 volt. This difference is greater than this over voltage. That means that cobalt 3 plus come in this region below this line, so it can oxidize water to oxygen. If it come in this region, there will be no reaction because water is stable there. Now in another case, we have a good oxidizing agent, dichromate. You have already studied about dichromate in your lab experiment. Also you have used dichromate as an oxidizing agent in your third and fourth semester for volumetric analysis. Dichromate is a good oxidizing agent in acidic medium. It has a potential of 1.38 volt. So 1.38 minus 1.23 means 5.15. Excess potential is only 0.15. Then that species will come in this region. So due to our potential, liberation of oxygen is not possible, or dichromate cannot oxidize water. But cobalt 3 plus can oxidize water because the difference is greater than the 0.6 volt. But in dichromate, difference is less than 0.6 volt and it cannot overcome the over potential barrier, so liberation will not takes place. That's why we are using water as a solvent for the oxidation of dichromate. If dichromate is able to oxidize water, then water will not be a solvent for the oxidation purpose. You have to remember this fact also. With this, we can conclude that this is the stability region of water. Why this region is marked separately? Normal water has a pH between 4 and 9. So this is the normal water region. If we consider saline water, it can be shifted to this region. When we consider acidic region, acidified water, this come in this region, that is also stable to some extent. But if they come in contact with some species of higher potential, then they oxidize water. If they come in contact with species of low reduction potential, then they can reduce water to hydrogen. These are the stability discussion of water. It is only thermodynamic stability, it does not explain the kinetic stability. Thank you.